you notice carefully, it just ends up being the magnification of the first lens times the magnification of the second. The first lens was, what did we say the first image magnification was?
We didn't ever say it, but it was 2.5.
2.5. And then we got 2. 2.5 times 2, 5. So if you do the math, it's easy enough to see, but you might just know that this value is equal to the magnification produced by the first lens times the magnification produced by the second lens. So that's like an easy thing to look for. If you want to lie without doing all the other crap, you can go right there if you know that information. Of course, it assumes you still know I and O for both of them. Now, a problem as we approach break, how much bigger does the final image look compared to the original object? It's physically bigger. But that doesn't necessarily mean it looks bigger through this two-lens system. That's a different issue altogether. Does it look bigger? Does it look smaller? What does it look like when you physically look at it? How would we figure that out?
That's where you bring in your angles. Base and trig.
This is what we call angular magnification. If you want to know how big something looks relative to the original object, what you do is you say, okay, here is Russell's bloodshot eyeball right there. And he's looking at this stuff. And as I look through this two-lens system, I see an object that's about, it takes up about this much space as I'm looking at it. And as I look at this one, wow, it extends a lot farther. The angle from the optical axis is huge. So how might we determine how big the actual object looks like? You get the angular magnification, call it m theta. We just take the ratio. It's got to be a negative, but we take the ratio of the final image distance. So in this case, it would be I2, the final image. Maybe I just better say that. Divided by the angle of the object, the original object. So that ratio, as you look at it angularly, will tell you how big or small something looks like. And it's the same principle as taking like a dime or a quarter and putting it in front of the moon. You can hold it in a spot where you completely eclipse. Well, heck, the moon eclipses the sun, right? But the sun is vastly larger than the moon. But because the moon's closer, it typically has a larger angular breadth than the sun does. But it's disproportionately farther away relative to its radius or its diameter. So let's figure out what this value is. How much larger, how much smaller does this final image look? Well, to figure that out, if we presume that the eye is basically, for all practical purposes, right up against the lens, so we're looking at it. So we're not really looking at it from back here, we're looking at it from here. We could always add that, but I don't want to deal with that extra value.
This is the assumption, like on a microscope, right? When you're turning the little thing to the next lens over, it's assuming right from where I mean, it's not assuming your eye is back a quarter inch.
Correct. It doesn't adjust for how far away you're putting your eye. It's assuming your eye's right up against it for all practical purposes.
Ouch.
Which is why magnification is never fully exactly what it says when it says 10x or 100x. It's relative to the plane of the final eyepiece lens. So what we need to do is we need to if I were to draw a straight line to the original object, I want to compare this angle here, which is the angle of the object, and I want to compare that angle to this angle here, which is the angle to image 2. And by the way, it's the same as this angle. The nice thing is that it follows the principal ray 3. It's kind of nice. We got different values that we can use to calculate that, and we should presumably get the same answer. So the original object angle would be 70 plus 200 centimeters on along the optical axis. That's how far away it is. And by the way, I'm going to have to go ahead and convert some values into either meters or centimeters just to keep things consistent, so we don't. So it's going to be 10 centimeters divided by 270. Where that value is. Pretty tiny. 127.
This is like 13 times magnification almost.
Angular magnification.
Yes.
So stated, the final image is negative, what did we say that final value was, 50 centimeters? Or point, this was meters and this was meters. Yeah, I made that flop myself. Final image is a half meter size, not a half a centimeter. Start out with 10, it's bigger. So we have, actually the units cancel out anyway, but we have 50, negative
Oh, I
50.
get this wrong then.
What's that?
I accidentally have that as 25 over 50 instead of 50 over 25.
We take the height,
Which means it's actually a lot more.
and then we divide that by, what did we say, was it 25? I'm using the right number too.
Three
That's
times
going to be negative 2. And by the way, the units would be radians. This is just and by the way, 2 radians. Now technically it's the sine, right? But for small angles, the sine and the ratio are the same value. 2 radians is actually pretty large. You can't do that. You can't do that.
Yeah, because this angle's pretty fat, right?
Yeah, so let's do it the right way.
Let's just use the inverse tangent.
Yeah, so take the inverse tangent. Let's hope we get away with it, but that's a pretty huge final. So let's not shortcut. So we have 10 divided by 270. That's one number, and that's going to be close to 1/27th of a radian. And then for the final image, we have to take the inverse tangent. That is it's a lot larger, so we have negative 50 divided by 25. And the units cancel out anyway, so we won't deal with those. We have to deal with those. You have to do it in radians, not degrees. I guess they would scale the same, but I would use radians just. I guess they do. They scale the same way, so it doesn't really matter.
You got 2.12 and 63.4. In degrees. Certainly not in radians.
So this is, what's this one then?
2.12 degrees. If you want it in radians, I'll change it for you.
In radians, it's 0.04.
Degrees is just a little more intuitive.
Basically multiply by pi divided by 180, so it's
Right.
divided by 100 by 130, give or take. 160. Or 60.
Either way,
Oh,
your ratio is
okay.
going to come out the same.
It's tiny. Yeah, yeah. So
Which is 29.9.
See, that small angle approximation doesn't work very well for large angles, does it?
Same number.
One.
Well, one of
No.
them's one significant digit, and the other one's two, so.
Yeah,
What was the
one.
next number over?
It was 0.037.
Now, if we want to be more precise, 7, do it that way. We're measuring it to the same precision. Remember,
Like it's-
significant figures, you gotta decide what your significant figures are based on. Are they based on the decimal place, or are they based on the actual values? Kind of that is dependent on the precision of the measurements. And the problem would be, how well is this value known compared to how well this value is known? I would suspect under normal circumstances that we would know things to maybe a millimeter, or even the nearest centimeter, I guess. So you'd have 3, 2. This answer would be 2 significant figures. We need to keep the 7 anyway. And then here, if there's either 2 or 3, so you'd be 2 or 3 there. Your final answer, regardless, will be 2 significant figures if you want to think about it that way. However, you want to keep all of the calculated values and not round until the very, very end.
Yeah.
Otherwise, you're going to shortchange yourself by almost 10% in this case. And 0.37 and 0.4, it's 0.003, that's almost
And
10%.
two sig figs, you have to be like 30 points.
So we have negative 1.11 divided by 0.037, and now you get the number is 13 or something?
No, it's 29.9 or just 30 and two sig figs. Yeah.
And if you think about it, that actually makes a lot of sense. I mean, if you were trying to look at some speck here, that speck there, relatively speaking, would be like that big there. So you'd be able to see it blown up. That would be maybe advantageous. Now, just a little practical note. As we think about this type of arrangement, and we're going to do something very similar. You guys will do something very similar in the lab tomorrow. There's one big problem if you were experimentally looking at this. What might that be? Final image is virtual. You can't find it. You can't put it on a projection screen to measure it. There's no direct way to measure it. It's hypothetical, if you will. Your eye sees it, and it's certainly a larger image. But from a practical perspective, this isn't something you put on a projector screen and see it. Where would we have to move the second lens in order to get any kind of image that we would see? What's the requirement to get a real image for any positive lens?
The object has to be outside the polyfocal.
Yeah, the object better be outside of f2. It's the only way you're going to get a real image. It doesn't matter if the first image is virtual or not. It makes absolutely no difference whatsoever. In order to get a value you can see, you need the final, you need the first image to be outside of the focal length of the second lens. And those are the conceptual things to think about. So I'd have to move this lens then back so that wherever that original image was, which was over here somewhere, I have to move this guy, or I have to move this lens so that I have to move F2 onto the other side. So what I'd like you to do is maybe blue would be nice there. I'm going to take a break, but come back, move the second lens over. How about 50 centimeters? Add 50 centimeters. It doesn't matter, any value more than 25, right? Because you got to just overcome this distance. If you make it 25, then you got kind of a problem because you take one of the focal length and subtract one of the focal length, you get 0, so you have to
Yeah,
use a
those
lot of
parallel.
decimal places. But you have to be a little bit off. They have to be at the very, very least on the opposite side, 0.0001 at the minimum centimeters that way, 25. So just put 50 on the other side, and like you guys, when you come back, just take a short break and go through this problem. It's a simpler version. It's the version that you'll use in lab. But this is typically one of the main complications, trying to figure out how to deal with these two-lens systems, because it blows the mind. And I'm also going to move it over after we do that, just to give you something to think about. I'm going to put this lens over here maybe, and see what that does to the final image and how we have to predict its value. We got some things to do. But we'll do that in a moment. So we're going to take a break now, and we'll come. It's fun stuff.
I forgot yesterday to